Okay, well, let's get started. So today we're going to look at factor analysis, um, both exploratory and confirmatory. And typically, exploratory is just abbreviated FA, confirmatory factor analysis, CFA. But essentially what we're doing when we do factor analysis is we're reducing the amount of data that we have. And so what we're going to do is from unobserved, or we're going to create unobserved variables from observed variables. And these unobserved variables we call latent variables. So we'll talk about exploratory factor analysis first. And so we apply our methods, or factor analysis methods, to a set of observed variables. And what we want to do is find underlying factors, the latent variables, from which the observed variables were generated. When we do exploratory, obviously, as the name implies, there's no pre-specification of the factors. We're going to allow the program to generate the groups of variables that define a factor. And so this is obviously confirmatory factor analysis is sort of the opposite of this, but we'll get to that later. When we do factor analysis, the data that we're going to start out analyzing is the correlation matrix of variables. And so here's a correlation matrix of 22 variables. Obviously, I didn't have room to put the remaining ones to the right hand side here, but it would be a 22 by 22 matrix, and this is the lower half of it. And as you're probably familiar with correlations matrix, that the main diagonal is all ones, because that's the correlation of a variable with itself, which is a correlation of 1. And then there's correlations that would range from minus infinity through 0 to plus infinity. Well, no, not infinity, but from -1 to +1. So this is the data that factor analysis is going to work on. And so I have a set of data here. It's actually real data, and it's 22 variables that relate to being overweight and how a person feels about that, different aspects of that. And so when we apply our factor analysis program, and we want to, of course, obviously, you're going to have software to do this. You don't want to do it by hand. We come up with these 22 variables with 13 factors. And the numbers that you see here are what we call factor loadings. And so the way that factor analysis works is that factor 1 is the most important, factor 2 is the second most important, and so on. And you can sort of see this by looking at the factor loadings, that as the number of factors increases, that as we get down to factors 10, 11, 12, and 13, you can see that the factor loadings are very small. So one of the statistics that we want to look at is what's called eigenvalues. And you can see in the previous slide when I had 13 factors, well, that's out from 22 variables. So that's 13 factors isn't all that useful. So what we want to try and do is see if there are, if we can reduce that number to the most important factors. And the statistic that's going to tell us that, or help us decide that, is what's called an eigenvalue. And so in our equation of AX equals lambda x, where lambda is an eigenvalue of A. And what that tells us is whether the vector x is stretched or shrunk or reversed when it's multiplied by A. And so what we want to find are the eigenvectors that don't change direction when multiplied by A. And then the solution vectors are going to stay in the direction of that fixed vector. And then we are going to look for the number that might be different with different factors that multiplies x. Probably the best way to sort of illustrate this is in a couple of the concepts of factor analysis is just with pictures. And so this is a common illustration of eigenvectors or eigenvalues that you'll see if you get online. This is the Mona Lisa. The left-hand side there is where you have a two-dimensional, where the vertical and the horizontal are equal. In the right-hand side, though, we've shifted the axes. So now that the picture looks slanted, obviously, where the red arrows now change directions, it's shifted to the right, but the blue arrow has not. It's still the same. And because it doesn't change direction, its length is unchanged. And in that case, if it doesn't change, its eigenvalue is 1. And so if you're really interested in the computations of this, you can Google it online or find a textbook. But anyway, what we want then to look at in our factor analysis is the eigenvalues and the most important factors that come out of the analysis is going to be identified by eigenvalues that are greater than or equal to 1. And so here's output. This is from Stata, but the output is going to be the same for any statistical package you use. It might be in a different format. But so we see here that we have 265 observations. In other words, 265 subjects or patients or whoever we're measuring here. And I might add that in doing factor analysis, you need a fair amount of individuals responding to your questionnaire or your survey, because the number of patients is going to potentially limit your factor analysis. So obviously in this case, if we have 22 variables and we only have 10 patients or 10 subjects, it's not going to work. And then so you can see that our retained factors are 13. We have them listed here. And you can see that for each factor of the 13 factors that were identified, we have eigenvalues. And you can see that the first 3 factors have the highest eigenvalues, and they're all greater than 1. So this tells us that out of the 22 items in our survey or a questionnaire, we can generate 3 factors that are important to look at. So we can disregard however many other factors there were, because all the eigenvalues are less than 1. And on the right-hand side there, we have the cumulative proportion of variance accounted for. And so you can see that these first 3 factors account for almost 70% of the variability in our data. So we're going to look at these 3 factors, and another thing that you get that most statistical packages will plot for you is what's called a scree plot of the eigenvalues and the number of factors. And so I'm not sure how helpful this is for the previous output told you all you need to know, but So you can see that we have three factors that have eigenvalues greater than 1. So the next thing that we're going to do is we're going to rotate or do a rotation method. And it's the idea that the axes of the factors can be rotated within the multidimensional space. And what this does, it's going to determine the best fit between the variables and the latent factors. And so the program looks at the strongest correlations between variables and the latent factor, and it calls that factor 1. Visually, you can think of it as an axis 1. And then it looks for the second set of correlations that are the second best, and so on. And so if we have factor 2, that would be, we call that axis 2. And if you have axis or factor 3, then we've got axis 1, 2, and 3, which then gets difficult to plot because you're in multidimensional space. Sometimes you'll get in unrotated solution that has strong correlations of a variable with several factors. In other words, maybe it looks like the variable is going to load on more than one, or a variable is going to load on more than one factor. Or you might find that no variable loads on a factor, or a particular variable doesn't load on any factor. And so that's why we do the rotation, because we want to make the actual data points fit the model better. And so the rotation will potentially make the factors more easily interpretable, although that's not always the case. Again, we can illustrate this by a picture here. So if we have two factors here, and the ones in black are the horizontal will be factor 1, the vertical factor 2, and the particular data points, then the individual variables that we have, you can see that if we rotate the axis, rotate it to the right, then that rotation makes all of the points closer to the axes, and better identifies the variables that load on the particular factors. So that's what we mean by rotation. And there are different rotation methods. I think most statistical programs that I've done this with, a method called Varimax is usually the default. There are other rotation methods that can be used, several, but the thing is, different rotation methods can result in, result in different results or different sets of factors. So in one sense, that's, if you are doing exploratory factor analysis, but you have an idea what you want to find, then maybe you're we'll make a different choice of rotation methods. Okay, so here's our rotated factor loadings for the 3 factors on our 22 variables. I'm not sure, like the first one is some sort of rating, so as an overweight person, and I don't recall what it is after that. But anyway, this is from a set of data where we had over 250 participants. And so here's the 3 factors and the factor loadings of each variable on each factor. And so when we've rotated it, then each variable will load on one particular factor. And when we talk about factor loading, we're talking about the absolute value. So for example, in the first item, you can see that it loads on factor 2, not factor 1 or factor 3. It's a negative value, but it's in terms of absolute value, it's the largest. So this is going to load on factor 2. And you can then see that there's a group of variables here that have the highest correlation compared to the other, or factor loading compared to the others. And so here's the set of variables that load on factor 2. Now when we get to the bottom of the list here, we'll see there's a potential controversy, but at the very last item has a loading of 0.5, which is the largest, but we'll come to that in a minute. So these are the variables that constitute factor 2. And then the same thing with factor 3, we can find the largest in terms of absolute values that are the largest factor loadings that define factor 3. And then the same thing with factor 1. And so you can see that if you go through each variable, each line, you can see that the largest correlation is related to the particular factor. Now, as I mentioned, there's something of a potential issue here anyway, that if we look at this factor loading for the last variable, it actually loads on factor 2 because that's the highest, it's 0.5, but its loading on factor 1 is 0.46, which isn't that much different from 0.5. So, oops, went the wrong way. Here's where you can maybe kind of manipulate things to sort of strengthen your case for what the factors are and what they mean. So it's possible that the last factor, we could have it load on factor 1, even though it is the highest factor loading is for factor 2. So there's the variables, all of the 20 or all the items and the factors that they load on. So now with our 3 factors, and I've included the 0.5 on factor 2 here, not the 0.46. So now we have the 3 factors, and so the next step is to identify what these 3 factors are. So typically what you do is you give them a name. And so maybe factor 1 is related to body image, factor 2 is related to relationships, and factor 3 is related to job performance. I just made those up. I'm not sure that's what they actually are, but anyway, you name these by, if you have no idea to start with, then you can examine the individual items and see, okay, maybe these items relate to body image, and these set of items relate to relationships and so on. So again, that's something that you as the investigator would do. And like I say, you might have kind of preconceived notion of what should be the factors that fall out of this, but if you don't, then you would have to look at each individual factors or each individual items and see what they might mean when considered together as a factor. So basically what we do, then we've reduced 22 variables to 3. And so for each subject in your data set or each patient, you can compute a factor score. And you can see that's sort of a regression type of equation there, where the lambda is the factor loading. But each subject will have a unique factor score. And so then you can analyze the 3 factors instead of having to analyze 22 variables individually, which you don't really want to do. And so what you're going to analyze then are the 3 latent variables. So we can do this several ways. Maybe we want to analyze each factor separately. So for example, maybe we'll analyze factor 1, where we're going to look at independent treatment groups and whether there's a difference between the groups on factor 1. Now, if X, the treatment groups, are dichotomous, that is, they're just 2, then that's just a t-test. Otherwise, it's an analysis of variance. Or maybe we want to include a covariate. And so maybe we're going to say factor 2 is equal to age plus the treatment group and the age by treatment group interaction. And so that's analysis of covariance. And the covariate can't be a variable that you've used in the factor analysis to begin with. If you analyze each one separately, then you potentially have the issue of inflating the type 1 error rate. So legitimately, you can't really test each factor separately at 0.05. You'd have to make some adjustment for multiple testing. But one way to avoid that is to do a multivariable analysis of variance, or a MANOVA. And so in that case, our outcome is a linear combination of the 3 factors. And I've represented that by the matrix of the 3 factors here. Of course, the thing with the multivariable analysis, that although you can get an idea of which one is more important or which one is making the difference in your analysis, but in this case, if we have 3 factors, doing the MANOVAs probably would be the best way to start out anyway. So that is exploratory factor analysis. Now we want to look at confirmatory factor analysis. And now the difference here is that you as the investigator are going to determine which variables define the latent variable. And so obviously, as the name implies, what we need to do then is to confirm whether the data, the variables that you selected, fit the model. And as true of exploratory factor analysis, the relationship between observed variables and the latent variables are assumed to be linear. And so the observed variables then are going to be linear functions of the latent variables. And so in the same way that we are similar to the exploratory factor analysis, we have our observed variable X is equal to lambda, the factor loadings, the underlying factors, and then measurement error. The fact that they're bold means that they're matrices and not individual variables or terms. So when we look then at, when we are doing confirmatory factor analysis, then what we want to do is then evaluate how well our model fits, or how well the data fits the model. And so there are different 4 or 5 different statistics here that we're going to calculate to evaluate how good our model is. And one is what's called the standardized root mean square residual. And this is the average difference between the observed correlation matrix and the matrix predicted by the model. So what you are looking for here is a value that's less than 0.08. And 0.05 is actually kind of what you sort of hope you get, because it tells you there's a better fit. If it gets above 0.05, and then especially above 0.08, then you don't have that good of a fit. The SRMR is not calculated if there's missing data. So, and that's a whole nother issue, whether you have missing data and whether you want to fill that in by multiple imputation before you do the factor analysis. But anyway, so this another is what's called the root mean square error of approximation. And this is an adjusted chi-square statistic that evaluates the model fit in relation to a perfect model, but it does penalize model complexities. And so what you're looking for here are values hopefully 0.05 or less, but at least between 0.05 and 0.08 indicates a reasonable fit. But if it's greater than 0.1, then you'll have to conclude that you have a poor fitting model. Then we have a couple of fit indices, the comparative fit index and the Tucker-Lewis index. And both of these indices compare the fit of the specified model to the null model. And so what you want here are values that are close to, or that are fairly large, that are close to 0.95 to 1. And the values below that are going to indicate that you don't have a really great fit. The primary distinction between the CFI and TLI is that the TLI penalizes the model complexity, whereas CFI does not. And then you come to the chi-square, or the likelihood ratio test. And for looking at confirmatory factor analysis, this is the most important statistic that we want to look at. And so the chi-square, what you want is a chi-square that's not statistically significant. Ideally, in model fitting, you want the chi-square to equal the degrees of freedom of the chi-square. That probably never happened, but you want it to be non-significant. And this is true in any type of modeling where you do a likelihood ratio test. In regular hypothesis testing, you want a p-value that's really small. That's what we call statistically significant, typically 0.05 or less. But in model fitting, where you're looking at a predictive model, you want a non-significant chi-square. Because if it's significant, that tells you that there's not a fit. And in confirmatory factor analysis, this is the most important statistic that we'll look at. And then the last one here, the coefficient of determination, or this is the R squared value, the percent of variance that's accounted for by the latent variable. And so as in regular regression, you want a R squared that's getting close to 1. Typically 0.7 or better is considered a good number to shoot for. I consider 0.8 is even better. So those are the 5 different statistics that we're going to look at to evaluate our model. So here's a schematic of confirmatory factor analysis, and we call this our measurement model. And so in this example here, I'm looking at whether we can consider all 22 items as indicating a general or an overall quality of life latent variable. And in this kind of schematic here, the latent variables are always indicated by ovals. Rectangles indicate the observed variables. And the circles indicate error variances of each of the variables. So what this is going to give us, in addition to numbers related to the error variances here, is going to give us factor loadings. In other words, the factor loading is represented by the unidimensional arrow from the latent variable to the observed variable. And so we're going to get a number that tells us what this loading is, how strong it is. And then another thing that we can actually change and maybe get a better fit of the model is suggesting that there are correlations between some of the variables in our model. And so the bidirectional arrows represent correlations. And so here you can see that I've suggested that there's a correlation between the first and second variable, the second and third, the third and the last, and so on. And as I mentioned, you can indicate different correlations, what you think might be correlated, and those will sometimes really improve the fit of the model. So this is what confirmatory factor analysis will look like as a schematic. One of the nice things about Stata is that you can actually just draw this diagram, put in the observed variables, and Stata will generate the syntax that estimates the factor loadings and the error variances. Some of the others might do that too. I would guess they probably do, but I'm not sure about that. So here, looking at our 22 variables and whether that could, those 22 variables could identify a, say, a quality of life latent variable, we see that we don't have any kind of fit at all. Our likelihood ratio test, our chi-square, is significant. The fit indices are not anywhere near 0.9. The only good statistic is the R squared. And you can realize this, that or realize that in doing this test for how well your model, the data fits your model, it's the chi-square that's the most important one. And so you can get these other statistics that look pretty good here. None of these do except for the R squared. And we don't have the SRMR because we have missing data in this data set. But our chi-square tells us that these 22 variables can't be used to identify a single quality of life measure. So I'm going to give a couple more examples here to illustrate this. And so these are items from the Promise 29, the Patient-Reported Outcomes Measurement Information System. And I'm not terribly familiar with this, but I'm assuming the 29 means there's 29 items that you probably rate on a rating scale. But these are person-centered measures and evaluates physical, mental, and social health. And there's forms, I think, for both adults and children. And it's often used with looking at individuals with chronic medical conditions, although it can be used in the general population as well. It's a well-established measure. If you're looking for a measure to, or an instrument or a tool to measure these sorts of things, this is a good one to use. So the Promise 29 has 7 domains: social roles, anxiety, fear, depression, fatigue, pain interference, physical function, and sleep disturbance. And so you get a score for each one of these domains. For social roles and physical function, a higher score means you're doing better. For the rest of them, anxiety, fear, depression, and so on, a higher score means you're not doing as well. But anyway, these are the 7 domains that we're going to look at to see whether or not we can define a latent variable that we'll call quality of life measurement. And so you see here that I have the factor loadings so with social roles, factor loading is 0.84. With anxiety, it's a -6, and so on. And you have a positive one with physical function score, which you'd expect, but negative factor loadings on all the others. Then we have our error variances here, and then I've put in a couple here where I think there might be correlations. So obviously, I would guess that there'd be a correlation between fear, anxiety, and fear and depression, and there is. It's 0.55. And then a correlation here between fatigue and sleep. And again, there is some correlation here. But anyway, so what we want to do then is we want to look at how well the data fits the model. And so when we look at our likelihood ratio test, we see that we don't have a good fit because we have a significant chi-square. Now, the root mean square error of approximation is kind of close. We have really good statistics for the fit indices and the R squared, and the 0.058 for the SRMR is pretty good, not too bad, but our so we have pretty good statistics, some really good statistics for the fit indices, but because our chi-square is not non-significant, our model is not a good model to use. That is, we can't use the 7 domains to identify one latent variable, and I believe that's why each of the domains is typically analyzed separately. Okay, so here's another the last example I want to give here is a measurement of activity. And in this case, it's measuring leisure activity. And so it's measured as vigorous, moderate, or light. And it's measuring it in the summer and in the winter. Not sure why they left out spring and fall, but maybe it's because they would expect summer and winter to be the times when you would exercise the least or engage in leisure activity. So anyway, again, we'll call this leisure activity, our latent variable. And so again, here's our factor loadings, which are really pretty good, and then some correlations that I thought might exist. Again, here the correlation between the summer vigorous and the I guess this would be the light in the summertime is not real great. So it may be that I could get a better fit if I took this one out, but we'll leave it in for now. Whereas you can see the correlation between light activity in summer and winter is highly correlated. So what we want to look at then is how good this model fits the data, the 6 items about leisure activity. And so if we look at our goodness of fit, we can see that this is doing really great. So we have a chi-square of 3.29 with 4 degrees of freedom. That's not significant. The root mean square error is virtually 0. The fit index is perfect 1, and our R squared is extremely high. So in this case, we can conclude that we can put all these together in one to make up one latent variable that we'll call leisure activity. Now, in the context in which we're actually doing this, we're looking at leisure activity. We're looking at exercise activity and one other, which I can't remember offhand. But anyway, we have here, at least for leisure activity, a really good latent variable to use in our analysis. Then, so what we might want to do then is regress some predictor variables on the latent variable, in this case, leisure activity. So I've picked out 4 variables here: age, BMI, income, and education, data that we have. And so we want to see if these variables predict or how well they predict leisure activity. And so here's our model. And so if you remember that we have a really good measurement model, that these over here measuring leisure activity had a really good fit to the data. But now we want to look at whether age, BMI, income, and education impact leisure activity. And so, again, we have now our standardized regression coefficients, which means that these are correlations. And so we can see that age and BMI have a negative impact on leisure activity, which is not terribly surprising. Income and education have a positive impact on leisure activity. And then I put in the bidirectional arrows over here between the predictor variables. And actually what this means is that I'm including the interaction between, say, age and BMI, age and income, age and education in the model, as well as each one individually. So now when we look at this model, the regression model, we're not particularly interested in all of the other statistics except the R squared. And you might say, well, this doesn't look very high here as far as income and its correlation with leisure activity, but it is statistically significant. And the standardized regression coefficient here, that indicates that these are correlations since they're standardized. But all four of these are statistically significant. So that's, in a sense, the good news. The bad news is that we have a very disappointing R squared of 0.15, which means that our four variables are only accounting for 15% of the variance in the leisure activity latent variable. So I hope that gives you kind of an idea of what we, when we talk about confirmatory factor analysis, what that's about is determining how well our variables indicate a latent variable, and then we can do regression types of things with that. And so here's and this is actually what we call structural equation modeling, which confirmatory factor analysis is. So this is a really complicated one. So on the right-hand side here, our observed variables are leisure activity and then exercise. And so we want to determine three different latent variables from these measures: frequency, duration, and intensity. And then we're going to then use these three to define physical activity in general. And then we're going to look at predictor variables over here in a regression sense, but we're going to group these into latent variables themselves. So age, education, working, and married. So we'll call that social status. And then we're going to look at a latent variable called discrimination. And this might be racial discrimination or discrimination based on a person's weight. And then finally, mental health, which we're going to use measures of depression and anxiety. So now when we do this model, it's actually quite a bit of work, because we have to check out whether these three latent variables here are properly defined by these observed variables. So we have to do check out our measurement model with these. And then we have to check out our measurement model, whether these three actually can be used to define a latent variable that we call physical activity. And then we have to do the same on the left-hand side over here. We're going to have to determine how well these observed variables define the latent variable here. And then finally, and so we have to do that for all three. If all that works out, then we can then see what our regression here of three latent variables and their impact on physical activity. So that'd be a fairly complicated analysis, and would take quite a bit of, work to do. In the actual study that we're doing here, this is sort of where we want to head, but of course, whether we can actually get there or not is another question. So in summary, then, factor analysis is essentially a data reduction technique, and we're going to create what we call latent or unobserved variables. And we've given examples here of exploratory versus confirmatory, and in both cases, we're asking, does the model fit the data, or does the data fit the model? And then we looked at key statistics. So for exploratory factor analysis, our key statistics are the eigenvalues. That's going to tell us how many factors are really important. In our confirmatory factor analysis, then, our most important statistic is going to be the chi-square, and it's going to be a non-significant. We want a non-significant chi-square. And then if we're going to do any regression type of modeling, then the statistic that we're really interested in there is the R-squared. And as I was preparing this, I remembered some years ago at a conference. I can't remember. I don't think it was a statistics conference, but it might have been heart and vascular. But anyway, the investigators were doing this type of thing where they were looking at a predictive model. And in their conclusions, they had a chi-square that was statistically significant, and they said, oh yeah, look, it's statistically significant, when in fact they really wanted a non-significant chi-square. So I think they probably didn't really understand the idea of predictive models. But anyway, that's neither here nor there. But it is important to remember that when you're doing model development, predictive model development, the chi-square statistic needs to be non-significant. So in terms of software, all the major software packages, I think, will do this. In SAS, it's a package, or it's the routine called Factor. I know that does Exploratory. I'm not sure whether it does the confirmatory factor analysis, but I would think SAS would have that somewhere. In SPSS, it's a package called AMOS that does both exploratory and confirmatory. In Stata, the routine is SEM, which is structural equation modeling, does confirmatory factor analysis as far as structural equation modeling. I think Stata has a separate routine for just exploratory factor analysis, but I don't remember, probably factor or something like that. Anyway, in R, then it's a package called LAVAN, L-A-V-A-A-N. I haven't used that, so I'm not really familiar with that. But most statistical software will have routines in there to do at least exploratory factor analysis, and then a lot of them will have confirmatory factor analysis. So I've listed some references here. Some are really old, some are newer, a little newer, on both exploratory and confirmatory factor analysis. If you're really interested in it, just Google factor analysis, either exploratory or confirmatory, and you can find all kinds of papers and references. So I hope this has been at least somewhat helpful or informative, and I want to thank you for your time and attention. And as always, I will send the set of slides to those that deal with this, and they'll at Georgetown, and they'll send these out, the slides out to you. So we have a few minutes here. If you have any questions, I think what you use the chat for that, I sort of forget now. But anyway, If you do, I'll be happy to entertain them. I'll stay on for a few more minutes. Or if you'd rather just email me questions or even examples of factor analysis that you've done. Oh, see one thing here. Oh, okay. Yeah, so it's put out to folks at Georgetown. I send along these slides so they can get them to you. And then the second question, subjects for each variable, not factors, but each variable in your analysis. I think probably a better rule of thumb might be, 5 to 10. Because you do need a fair amount patient or subjects do factor analysis. You gotta have the data to do that. So in this case, 22 individual variables and you only have 10 patients, that's not going to work. In fact, you probably don't even get a solution for that. So you do need patients at least anywhere from 3 on up, preferably maybe 10 per variable, not per factor, but per variable. Okay, and so the question on splitting a data set. So I don't have a citation right offhand, but typically the splits are usually, if you have enough patients to do this, you either split it half and half, randomly select half the patients, run your model, and then try the model out on the second half, or a lot of times an 80-20 split is used. You develop the model on the 20% and then check it out on the 80%. Or you can do that vice versa. But anyway, those it obviously are random selections. You can't pick which ones you want in say the first half and the second half. You need to randomly select them. Okay, with that, I will close and we will meet again in November. Thank you for your time.